Hi there, this is Heath. We're starting Math 4175, which is cryptography. Welcome aboard. Let's go ahead and get started. In today's video, I'm going to spend a couple minutes talking about the course, and then we're going to go ahead and dig into some material for the first day. So my name is Heath. I've been teaching here at Virginia Tech for 22 years. This is the fourth time that I've taught this course, and I'm always enjoying teaching this course. Wish we were teaching it under better circumstances and that we could all be together, but I promise to make the best that we can of the circumstances. If you need to get in touch with me, you can get in touch with me with this email address. The math is optional, but if you include it, it routes to me a little bit faster. But I'll get it either way. And then this is the URL for the course, collegemath.org/cryptography. This is not on Canvas. We'll be using, over the course of the semester, some encryption and decryption tools that are online that can't be embedded into Canvas. And so we have this offsite URL. Go ahead and check it out. You can go ahead and download today's slides and the course contract and a couple of other little bits of information. All right. The prerequisites for this course, what you should have before coming into this course, is any course from this list. 34 is Intro to Proofs, Modern Algebra. This is Combinatorics. This is a 3,000 level linear algebra course. This is Advanced Calculus, Number Theory, and Mathematical Modeling. Not that the content of these courses are necessarily relevant, but the experience of having been through a rigorous proofs style course and not just a problem solving course is what we're looking for here. You should also have some kind of programming experience. I'll talk about this on the next slide. And if you're continuing on to 4176, the prerequisites are the same, one of these courses, but my recommendation is that you take either Modern Algebra or Number Theory, because those two courses do figure fairly heavily in 4176. And if you have had either of them already, you're just a little bit of a leg up. So they're recommended, but they're not mandatory. Okay. So as for programming, there will be coding assignments approximately every 2 to 3 weeks, which turns out to be about 5 coding assignments over the course of the semester. You can use any coding platform you want to complete these assignments. They can be general languages like Java or Python, or C++, or PHP, even if you want to try to use that. You can use special purpose platforms like Mathematica or MATLAB, if you want to do those. All 4 of these that I've mentioned up here, I can generally be some assistance in and troubleshoot if you want to come in and talk during office hours and ask questions about your code or something like that. If you choose something that's really esoteric, if you decide you want to write in machine code or some cutting edge language that I haven't ever heard of before, I may not be able to help you. So I won't restrict what platform you use, but if you go too far off the beaten trail, you may be very much on your own. We will be reusing code. Some of the earlier projects are to write pieces of code that we will then embed into a larger project later on. And so try to avoid changing platforms mid-semester, because if you decide partway through that you want to switch, then you have to go back and rewrite some of your earlier code. All of these platforms have some kind of cryptographic libraries available. That's not what I'm checking for, that you can, um, go into Python and say from this library use these functions, and then, answer the problem with one line of code. You need to be able to write your own routines for solving these problems. Don't use the cryptographic libraries. Other types of libraries are just fine, but just not the ones that trivialize the problems we're solving. Okay? All right, so let's go ahead and dig in. We're going to go through some terminology here and then look at two examples of crypto systems today. When we talk about information security, we're talking about a very broad field that not only includes cryptography, but other ideas like access control and virus detection and phishing and metadata and lots of other issues as well as cryptography. This is not a broad course. If you want to take a broad information security course, the EC department and the CS department both have one, and you're encouraged to check those out. We're looking specifically at encryption and decryption of data and the mathematical background necessarily to understand how those enforce rigor and things like that. So, some of the goals of cryptography include confidentiality. That is, we have some data or we have a message and we want to limit who can read this message or who can access this data. We don't want everybody to be able to see your grades. We don't want everybody to be able to look at your bank records or anything like that. We want to limit who can see it. And so we encrypt this data and restrict access to those people who have a certain password that can unlock that encryption. So that's the big part of the course. Chapters 1, 2, and 3 are going to be talking about different types of encryption schemes, their strengths, their weaknesses, some of the details of how we might implement them. Another goal of cryptography is data integrity. If we are receiving an email message with an attachment, for example, how can we assert that the attachment has not been altered between the time that it was sent and the time that it was received? That somewhere along the way somebody didn't intercept that package and replace that email attachment with a virus, for example. How do we know that throughout the entire chain of this email bouncing through the internet to get to its final destination, how do we know it hasn't been altered along the way? We will talk about how we can use cryptography to verify the authenticity of a message. And that's what we'll be looking at in Chapter 4. Okay? And then the later chapters will be for the next part of the course. So what do the two crypto courses cover and how they differ from each other? We said that a cryptographic system is symmetric or private key if anybody who knows how to encrypt messages can figure out how to decrypt messages, because the encryption process and the decryption process are so interrelated that knowing one gives you immediate information about knowing the other. In the first crypto system we're going to look at, the encryption process is simply to take your letter of the alphabet and shift it down a certain number of letters. So then the decryption process is to shift it back up a few letters. So anybody who can decrypt can encrypt, anybody who can encrypt, decrypt. We cannot separate those two roles within the system. Anybody who is an encryptor is also a decryptor. In an asymmetric system, the encryption process and the decryption process are so distinct from one another that it is not possible, if you know how to encrypt a message, you still don't know how to decrypt it. There is no computationally feasible process to be able to decrypt a message if you know the encryption process. The encryption process is a one-way process, and it takes a different kind of process to decrypt it. And as you can imagine, those are going to be mathematically more complicated, which is why we put those off to 4176. So 4175 covers symmetric cryptography, 4176 covers asymmetric cryptography. Okay? All right. Let's move on. When we're describing the implementation of a cryptographic system, or the weaknesses of the system, or some kind of detail about how it works out, we tend to involve three fictitious players in our discussion. Alice is the originator of a message. So Alice has to encrypt the message before she sends it. She's the encryptor in our system, and then Bob is a decryptor in our system. So Alice takes a message, sends it over to Bob, and then Bob has to then be able to decode that message. In addition, we hypothesize there's a third person in the system, Oscar, and Oscar is able to listen in on this communication channel without Alice and Bob knowing that he's there. And Oscar can observe whatever message is being sent and potentially alter the messages being sent as well. If Oscar can break Alice's and Bob's encryption scheme, the security of the message will be compromised. The book that we're using uses Oscar for this role. Some books call this third person Eve, which is short for eavesdropper. It is somebody who is able to observe the channel and possibly alter what's going on that channel. And is somebody that we do not want to have access to our message. So, all right. When we talk about a crypto system, formally a crypto system has 5 parts. And we abbreviate those parts with these letters, P, C, K, E, and D. Let's talk about what they are. P is a set of possible plaintext message units. P generally does not include the entire message. P includes whatever portion of the message is being encoded at a time. In the first crypto system we're going to just encode one letter at a time. And so P will just consist of letters. But as we get to more sophisticated crypto systems, we'll be able to include crypto systems that encode entire words at a time, or fixed length blocks of letters at a time, or maybe not fixed by the length of the number of letters, but fixed by the number of bits at a time, but some sort of unit that is being encoded at a time. The entire message will consist of multiple units in most cases. And then C is the set of possible ciphertext units that can come out of the system. Often P and C are the same set, but not always. Sometimes in their encryption process, we include some kind of statistical noise, some kind of padding, where we might take 3 letters of the message and encode them into a 5-letter string, which has then some extra noise in there to make it harder than for somebody to decrypt it back. So there could be some padding going on between P and C as well. K is the set of keys that we use to encrypt the message, the passwords to the crypto system. And in addition to these 3 parts, The other two parts are the encryption and decryption rules. The set E contains one rule for every key, and it's the rule that says how to use that key to encode the message from the plaintext into ciphertext. And then D contains a set of decryption rules. For every key, there has to be a rule that says how to use that key to convert the ciphertext back to the plaintext. These rules can be very similar to each other in a symmetric context. In an asymmetric context, they may be very different from each other. For obvious reasons, we require that the plaintext we require that the decryption key and the encryption key have to cancel each other out, so that if I start with a message and then I encode the message and then I decode the message using the same key, if I encode it and decode it using the same key both times, then I should get the original message back. Otherwise, there's not much value to the crypto system. We can't decode messages reliably. And so we have to check this condition in order to verify that this is a legitimate crypto system. Okay? So we have 5 parts. We have then the rule that the decryption key has to undo the encryption key. Okay? So let's look at our first crypto system. This is called the Caesar cipher or the Shift cipher. It is dates back to the age of Julius Caesar, and in fact was written about in memoirs about Julius Caesar. It is not the earliest known crypto system. If you want to go back even earlier, if you're interested in the history of cryptography, 2 earlier crypto systems are Atbash and Siddeley, but this is the one we want to start with because it's mathematically very simple to describe, and the other 2 are a little bit trickier. And in the shift cipher, we are literally shifting letters by a fixed amount through the alphabet. So Alice wants to encode this message: meet me tomorrow. She begins by taking every letter and converting it into a number between 0 and 25. A is going to be 1, B is going to be 2, C is going to be 3, so on and so forth. But Z is going to be 0 and not 26. This is a peculiarity that you might not be familiar with, but this allows us to talk about doing calculations in the field or in the ring Z mod 26. Okay? When we do this calculation, meet me tomorrow, M becomes 13, E becomes 5, T becomes 20. I'm sure you've done this kind of conversion before at some point. And then she and Bob have agreed secretly upon a key. In this case, the key is 12. And so what Alice is going to do is going to take every single letter in this system, in this message, and shift it by 12. I'll show that on the next slide. So when we add 12, 13 goes up to 25, 5 goes up to 17, 5 goes up to 17, 20 goes up to 32, and so on and so forth. We're adding 12 to all of these characters. But again, we have to convert these back into letters, and my letters only have numbers from 0 to 25. 32 is an overflow. It's bigger than the largest legal letter of the alphabet, and so instead of using 32, we subtract 26 from the sum, and that takes us back down to 6. 27 is an overflow. 27 minus 26 is 1. 30 minus 26 is 4, and so on and so forth. And so anytime by adding 12, we overflow our alphabet, we have to subtract 26 from the sum to take it back into something that's round. This has the effect of having the shifting wrap around from Z back to A, in other words. Okay? In fact, we can actually work that out. T, U, V, W, X, Y, Z, A, B, C, D, E, F. If we shift by 12, 1, 2, 3, 4, 5, 6 takes us to the end of the alphabet. 7, 8, 9, 10, 11, 12 takes us to the letter F, which is the sixth letter of the alphabet. What we're doing is we calculated that it would be the 32nd letter of the alphabet, but that's if we, go past Z. Instead, we just back up 26 and start over and get to 6 again. Okay? All right, so Alice has added 12 to every number in the message, and now she needs to convert these numbers back into letters. 25 converts into Y. 17, which we have twice, converts into Q's. The 6 that we have here converts into an F. And so on and so forth, everything converts out. And we have just arbitrarily added a space after every fifth letter. Just so that the spacing won't give Oscar any additional information, where just putting a space after every fifth letter just to form a pattern, but it doesn't have to be the same as the original spacing. So Alice sends this ciphertext to Bob. That's the message that she sends out. YQQFY, QFAYA, DDAI. So how does Bob decode this ciphertext? So that was the first 5 letters of the message. Bob will convert each of these into a number. So Y is 25, Q is 17, Q is 17 again, that's a 7, F is 6, Y is 25, and so on and so forth through the rest of the message. Bob knows that Alice had to add 12 to every character, so Bob is going to subtract 12. 25 minus 12 is 13. 17 minus 12 is 5. 6 minus 12 is negative 6. 25 minus 12 is 13, and so on and so forth. But negative 6 is an underflow. Our valid letters are only between 0 and 25. There is no negative 6 in the alphabet. And so what we have to do is we have to add 26 back to have it wrap back into the alphabet. And negative 6 plus 26 is 30. No, 20, sorry. There we go. So in encoding, because we're adding to the letters, we could have an overflow, in which case we have to subtract 26 to bring it back into range. When we're converting back, we can subtract 12. That may create an underflow, in which case we have to add 26 to bring us back into range. And then we convert numbers back into letters. So 13 becomes M, 5 becomes E, 5 becomes E, 20 becomes T, and there's the first word, and then there's the beginning of the second word. So Bob decodes the ciphertext by reversing the steps that Alice did. subtract 12 instead of add 12, and then correct any underflows that he obtains. Okay? How does Oscar, who can see this encoded message, decode the ciphertext? Oscar doesn't know how much the message was shifted by. But Oscar can do just brute force. There are only so many possible shifts. If we shift back by 1, Y becomes X, F becomes E. No, I have the original message wrong here. It wasn't YFFQY, it was YQQFY. There we go. If we go back by 1, we get X, P, P, E, X. If we go back by 2, we get what's before X, W, O, O, D, W. That looks like it could be something. Wood is a real word. But the rest of the message is going to turn out to be garbage. If we go back another letter, we get V, N, N, C, V. Keep going. U, M, M, U, B, U. That most of these shifts don't result in anything recognizable until you get to something like 12, and then that gets you to M, E, E, T, M. And then that starts looking promising again. Out of the possible shifts, almost always only one shift will result in a comprehensible message. It would be an amazing coincidence if 2 different shifts resulted in equally understandable, comprehensible messages. That most of these are going to turn out to be garbage. Okay? All right. So here's the formal definition of the shift cipher. Again, a formal definition has these 5 parts, P, C, K, E, and D. The individual units of the message that we're encoding are letters of the alphabet, which we're encoding as a number between 0 and 25. That's a set of integers modulo 26. If you have not seen work in modulo 26, addition modulo n in a previous class, and all of you should have, but in case you haven't, we will go over it formally in the next lesson. And then it just converts letters into other letters. So C is also the set of integers mod 26. And K is also the set of integers mod 26, but these numbers don't represent letters. They represent the amount to shift each letter by. So each of these is a number between 0 and 25. These represent letters. This just represents a shift amount. And then the rules in the encryption set is for every key, we just add that key into the message and then take the answer mod 26. The decryption rule is that we subtract the key and then take the answer mod 26. Okay? So these are my encryption and decryption formulas. So E sub 5 is equal to X plus 5, E sub 12 is equal to X plus 12, and so on and so forth. They're just sets of functions mod 26. So we still have to verify that the decryption and the encryption code, if we use the same key, gives us our original message back. Well, why is this true? Well, it's true because the encryption code using a key is X plus K, And then the decryption code using the encoded message is x plus k minus k, which turns out to give me my x back. And so that works. We get our original message back, and it was not, surprising that that's what happens. If you add an amount and then subtract the very same amount, you get your original number back. As our crypto systems become more difficult, there might be something to verify here that these two steps actually do cancel each other out. But in this case, the verification is very easy. Okay? A couple more questions. One more question, anyway. This is a weak crypto system. It's easy to break by brute force because there are only 26 possible shift amounts. But one key in K is especially weak. Which one and why? Well, as we define this, and you may have been wondering this earlier, we define all three of these to be the range of integers from 0 to 25. What happens if K is 0? K equals 0, I can run this through the crypto system. I can add 0 to my message. I can subtract 0 from my message. Bob is able to decode what Alice sent him, but no encoding actually ever happened. This one is especially weak because no encoding takes place, or no encryption takes place. Okay. All right. So let's look at a more complicated crypto system. This was called the substitution cipher. This time Alice wants to encode another message. This time the message is avoid main highway. And Alice has figured out that Oscar has decoded her last message. And so she and Bob have agreed to use a more complicated cipher. Instead of shifting letters by a fixed amount, we are going to replace every letter of the alphabet with a different randomly chosen letter in this order here. So this is the alphabet, and this is a permutation of the alphabet. And so they're not all being shifted by the same amount. And then using this substitution, the word avoid, A-V-O-I-D, becomes H-X-A-G-C. And that's our first word in the new message. And then main becomes FHGP, and then highway becomes WGYWEHV. And again, we're just putting arbitrary spaces so that we can look at this message in chunks of 5 letters, but we are not giving information about the size of the words by doing this, where this is now an arbitrary spacing. Alice sends this message to Bob. All right. So how are we going to define this crypto system the way we did for the shift cipher? So we have our plain text, our ciphertext, our keys, our encryption rules, and our decryption rules. Okay? So our plain text, we are still encoding one letter at a time, but we're not having to convert the letters into numbers. this time. We're just encoding on the actual letters. So it's a set of letters from A to Z. And they encode into letters from A to Z. The key is a set of all possible permutations of the alphabet. And if you have taken combinatorics, you know how many permutations there are in K. And we'll talk about that number in a moment. So the encryption rule is that if I have a key in K, that key is a permutation. And we often use sigma to indicate a permutation, but we can use other letters to indicate the permutation. Then the encrypted version using that permutation of a letter X will be the permuted version of the letter X. If you use some other letter, use permutations instead of sigma, that's fine also. Well, then what we have to do to get our text back, if we use the same key, the decryption rule for that permutation is not to permute the letter again, but to take the inverse of that permutation and apply that to X. Okay? And the inverse of the function will cancel each other out. The decrypted version of the encrypted version of the letter using the same key both times is sigma inverse of sigma of X, which is equal to X. So that is a formal definition for the crypto system. We have identified all 5 parts of the crypto system and verified that decryption and encryption cancel each other out. What is the size of the key space for the crypto system? When I say size of the key space, that's just another way of saying how many possible keys are there. So how many permutations of the alphabet are there? The answer is 26 factorial. 26 factorial is approximately 4.03 times 10 to the 26 power. So that's a gigantic number. Let's think about how large that number actually is. Suppose Oscar could crack this message by brute force. His computer can apply 1 million keys per second. How long will it take his computer to apply every possible key to the message? So there are 4.03 times 10 to the 26 keys. If we divide that by 1 million, which is 10 to the 6 keys per second, that gives me 4.03 times 10 to the 20th seconds. 10 to the 26 divided by 10 to the 6. I am dividing, I subtract the exponents, and that gives me 10 to the 20th. And that's approximately equal to 1.3 times 10 to the 13th years. So 10 to the 13th, that's 13 billion years. So it is not feasible to try to break a substitution cipher using brute force. That the number of keys is just so large that even with a fast computer, you can't possibly test enough keys to be able to hit the right one in a reasonable expectation of time. My last question is, though, that despite the fact that it takes a very long time to break this by brute force, the substitution cipher is considered to be insecure. What are some possible reasons for this? I'm not going to answer this question today. I want you to think about it and come up with some reasons why you believe the crypto system, the substitution cipher, can be broken faster than brute force. And what are the features of it that make it insecure? So think about this. Be ready to discuss this. We will be meeting soon, and I'm hoping that we can get some discussion out of that. All right. Thanks for putting up with me. Welcome to the course. I'll see you again on Friday.